This is RTP. This is RTP180.
Thank you, Wade, and thank you, Daniel, for the wonderful introduction. So never put videos in your presentations. So here's a disclaimer. I am not an astrophysicist. I'm not an astronomer. I'm not a cosmologist. I know about all these things barely enough to amuse masses and convince funding agencies. So, so here I go. So that's me, and I'm going to talk about exploring neutron stars on Earth. So instead of standing behind a large telescope, I stand behind a very precise and revealing microscope, and I'll tell you what that microscope is. So why study neutron stars? It is innate human nature that whenever we cannot reach somewhere, we want to know about it. And that's one of the reasons. So let me tell you what neutron stars are, and Daniel alluded to exploding stars or novae. So whenever a massive star, not a huge one, not 10, 20, or 30 solar masses, those kind of stars collapse in supernovae, which end up as black holes. But if your mass is somewhere in between, maybe 7, 8, or less than that solar masses, in the death of a star, they can collapse in a process in which the remnants are so-called neutron stars. And neutron stars, you can imagine a star which is in the process of collapsing, and in that process, the immense density essentially crunches the protons and the electrons together to generate bulk of neutrons. And the gravity is so immense that it is about a factor of 10 to the 12 or billions and trillions more than what is on Earth. And the beauty about this is that the size of these objects is about size of Manhattan. So you have essentially a star crunched into a little ball. And also imagine that if there's an ice skater and if he or she is collapsing into a single point while spinning, you have seen ice skaters start to spin very fast because of conservation of momentum. They pull their hands in and they spin very fast. So as these stars collapse, they actually spin really fast. They can go up to 40, 50,000 RPMs or revolutions per minute. Since the gravity is so humongous in these stars, the atmosphere is really thin. So the atmosphere around neutron stars is of the order of just few microns. So very thin atmosphere. And they are hypothesized to have very flat surfaces. The reason being that of gravity. So you will find mountain ranges on these neutron stars where the largest mountain you would find, the peak of it would be about an inch or two high. And as you go deeper and deeper into these neutron stars, from iron, you will eventually end up with lots of neutrons, and then there are exotic materials. And these neutrons exist in what is called superfluid state. So you can imagine a liquid neutron. I don't know how to visualize that, but it is a material which has no protons, there's no electrons, it's just pure neutrons just flowing around. And then there's other exotic objects inside it. As Daniel said, a few years back, we detected an event which happened 130 million years ago. Two neutron stars collided. And on August 17, 2017, at that particular time, there's a gamma ray monitor which triggered gamma ray. Gamma rays are very high energy photons, much, much higher than X-rays and what we see here. And so it triggered an alarm coming from outer space, and especially during these supernovae and creation of stars and neutron star collisions, you typically see these bursts of gamma rays. And a few minutes later, the LIGO, which is the Laser Interferometry Gravitational Wave Observatory, confirmed a merger event later on. And after that, what is called a multi-messenger campaign was launched to look at these neutron star mergers across the spectrum through light, proper light, the light which is in our normal vision range, to X-rays, to gamma rays, to all kinds of wavelengths. And there's a paper out there published by LIGO, and if you look at that paper, most of the things which are extracted about the nature of neutron stars requires knowing what is called an equation of state. And I'll tell you what an equation of state is in a second. But this particular event was pinpointed at a galaxy which is about 130 million light years away. And this is an image of that galaxy captured by Hubble. So what is equation of state? So if you see a balloon, the pressure and the volume relationship, or the temperature and the pressure relationship of that balloon, is its equation of state. Most of us who took any physics or science in high school or before, we remember this relationship PV equals nRT. How many of you know that equation? There we go. Or P1V1 over T1 equals P2V2 over T2, you know, all those things. Those are all equations of state. So how do you know that equation of state? Because it tells you that if the object is this volume, this is how much pressure there is. So it turns out that the densities which are relevant to neutron stars are similar densities as neutron-rich nuclei of atoms. So, thank you, Wade. So the nucleus is a very good, you know, the trick is not to break the sentence. He's waiting for you to break the sentence. So lots of commas. So the nucleus is a very typical object which looks like a neutron star, especially if you look at nuclei which are neutron rich. So the point is that in order to understand a neutron star, you look, instead of far out there, you look at what is underneath your nose, nuclei or atoms. And it turns out that there's a particular mode of living of these nuclei which exhibits equation of state or behavior which are very typical of neutron stars. And this is called in a mode in which the neutrons and protons are sort of going in a sort of a scissor mode within the nuclei. So what we do is, this is our microscope. It is on the campus of Duke University. This is world's most intense polarized source of gamma rays. How many of you know that in your backyard you have one of these machines? It's a free electron laser, and it produces high energy gamma rays, and we can use those high energy gamma rays to excite the nuclei in states for which we can study the equation of state. And it turns out that studying that equation of state for the nuclei, you can pinpoint or you can constrain the pressure of the neutron stars. So that's what we exactly do. So this is about, you know, like a horse race track, about the same size, and it produces gamma rays going that way using free electron lasers. So there's a lot of technology which goes into that, and I just wanted to point out, being in RTP, that we work at a consortium of all major universities in RTP, which includes diverse STEM training of minorities in STEM, especially with HBCU participation. And we use technologies such as accelerator-based, computational, electronics, solid-state, and big data sciences. Not only that, projects as such bring large amounts of money into the economy of RTP. Just this single project brought 1.5 million to our local economy in the RTP. So with that, I conclude that it is, this project is funded by the National Science Foundation through an Excellence in Research grant, and the operation of the laser is funded through the Office of Science, Department of Energy, and those are all the photos I stole. Thank you.